is going to tell us about topological gauge theory, quivers, and flow trees. So please go ahead.
All right. Does everyone see my slide?
Yes.
Okay. Okay, so thank you very much for the invitation to speak. And since it's the last talk of this workshop, I would like to thank Anna, Tom, and Andrea and Kento for putting together this nice workshop. Would ask everyone to give them a long applause, since it's in these difficult circumstances. It was a special effort, I think, to organize and going from in person to online, and so thank you very much for organizing this workshop. It's very nice.
We'd like to thank all the speakers for all the amazing talks. So thanks all for all the hard work.
Okay, so this talk will mostly be based on a paper from last year. I think I would have spoken about it when the workshop was 12 months ago. It's joint work with Guillaume Bouchard and Boris Pioli. And so a few subjects are coming together: topological gauge theory and quivers, and we use the technique also from flow trees. So let me start with the topological gauge theory. So it's of interest physically as a setting in which many aspects of quantum field theory can be analyzed exactly, and such as electromagnetic duality, confinement, effective field theory, gauge symmetry breaking. But at the same time, topological gauge theory also connects various subjects in mathematics, such as algebraic geometry and modular forms, etc. So today I will consider a twist of n equals 4, a supersymmetric Young-Mills, which has several possible topological twists, but I will consider the one known as the Waffa-Witten twist. We will consider the Fano fourfolds, which already appeared in a few discussions in the last talk by Pietro Longhi, and how this connects to Quivers. Okay, so let me just discuss a little bit this Waffa-Witten theory. So one can formulate it on any arbitrary compact smooth form manifold, not necessarily algebraic. So one can consider a principal bundle P, a principal G bundle for gauge group G, and then we have the usual gauge field strength F. And besides this field strength, there are a few other fields in the theory. Let me just comment on the bosonic ones. There is a complex scalar phi in the adjoint representation. Then there is a real scalar field C, and in addition, there's a self-dual two-form B+. So this is now the 6 scalar fields of n equals 4 Young-Mills are kind of reorganized after the Waffa-Witten twist, and you see that you can all these fields they exist for an arbitrary form manifold. Okay. So if one considers the theory, then one finds the following Q-fixed equations here at the top. So we have an equation for F plus a commutator of C and B plus the commutator of B plus and B plus, where the plus is the self-dual component of the field. It's for B is the field itself, but for F plus it's a projection. And then there is this a second equation, the D of C plus the D of the Hodge star of B plus is equal to 0. Now, in general, these equations have different components of solutions due to these extra fields, the C and the B field. However, if there's a constant scalar curvature R larger or equal to 0, then one can show that there is a vanishing theorem, and the C and the B field are equal to 0, which then implies that F plus is equal to 0. Okay, so this holds for the Fano manifolds and for the K-free surface, for example. And in this case, there's only the instanton component is non-empty, and then these solutions they saturate the famous BPS inequality, but they have a lower bound on their action. Okay. So yeah, just to mention that the UN instantons have famously one-to-one correspondence with semi-stable vector bundles. let us introduce some notation. I use this gamma for the churn character, or a vector of the rank n, and then the first churn class C1 and the churn character CH2, which is mostly negative. It's 1/2 C1 squared minus the second churn class C2. And we can consider the moduli space or moduli stack of semi-stable vector bundles with respect to some polarization J. Okay, so I will kind of skip over issues like singularities, but yeah, these are well discussed in the literature. Okay. So then this theory, n equals 4 Yang-Mills, is super conformal and has a UV coupling constant tau, which is this complexified parameter theta over 2 pi plus 4 pi I over g squared. And we can make this an exponentiated variable q as usual. And then the partition function or the path integral theory, one can show that it becomes a generating function of the Euler numbers of the moduli space. In this case of the Waffa-Witten twist. So let us take specifically this, for now, this case where the rank is 2. And then we have a first churn class, say noted abbreviated to mu, and let n be the second churn character or the instanton number. Then we can then the coefficients c mu of n of the partition functions are essentially equal to the Euler number of these moduli spaces, suitably well defined, and then basically the partition function becomes a generating function, h mu of tau. Okay, and for the purpose of this talk, or for now, I will restrict to x to the local the projective plane P2, but all the discussion actually continues with minor modification for other toric form manifolds, such as F naught, and the mirror of the non-compact Calabi-Yau local F naught is a local curve, and see the talk by Pietro for the relation to spectral and exponential networks, and to compute the PPS spectrum from that perspective. So basically, this goes back to the work of Waffa and Witten in 1994, together with work by Kliatschko and Yoshioka. As a result of this work, the following was found, namely that this generating function h mu of tau, there are only two independent cases. Mu is 0 and mu is 1, and it takes this form of this ratio of functions f mu divided by this product, which is the so-called eta function to the power 6, and then f mu is an interesting arithmetic function. It's a generating function of the so-called Hurwitz class numbers Hn. So it is for two cases. If mu is equal to 0, you get the class numbers modulo 4, and if mu is equal to 1, you get the class numbers -1 modulo 4. So it's intriguing that these moduli spaces of instantons, they are actually the Euler numbers correspond to these class numbers, and basically this power of the eta functions arises due to point-like instantons, or and then this fact the functions f, they are due to smooth instantons. Okay. So basically, these calculations followed an approach to kind of determining these Euler numbers, which I learned from the papers of Yoshioka, working over finite fields, fq. Sorry, this q is completely different from the q in terms of the tau variable, but it's hard to avoid this. It's the only place where this q appears this way, and the well conjectures. And the f mu in current language are examples of mock modular forms studied by, say, Ramanujan for over a century ago, and then other number theorists like Ye and Zwegers. Now it has been possible to continue this basically the calculation of these generating functions to larger n, more complicated or case groups un with n larger than 2, and also to generating functions which include the refinement parameter y, which enumerate the Poincare polynomials of these moduli spaces. And these are generalizations of mock modular forms. In fact, they are mock modular forms of depth n minus 1 for un, and they're studied quite a bit in the literature. There was also a paper by Putrov, De Bocker, and Witten with an intrinsic n equals 4 derivation of the mock modular or the non-holomorphic part. Let me also mention here that in joint work with Alexandrov, Banerjee, and Piolin, we used basically the Darboux coordinates and their integral representations, which were discussed in Nijtke's talk and other talks, to basically derive this non-holomorphic part of the partition function. So basically, the holomorphic part is not quite the full story, but I won't go into detail into those things in this talk. Okay, so just to kind of illustrate how these what one finds if one goes to partition functions for larger rank Gates groups. Here we have an example in the paper with Bojar and Piolin. We determined these generating functions for U5. Takes basically the following form, where all these functions on the right hand side are completely explicit functions, and you can make generating series for small q, and one finds then here on the right hand side the explicit Poincare polynomials of these moduli spaces. So for example, if you have a SU5 Gates group with a vanishing first Chern class, then for instanton number 5 you get a 26-dimensional moduli space, and you can really read off the Betti numbers. And yeah, in principle, this is known for arbitrary n. Okay, so this is one approach to vector bundles on P2 and other toric surfaces. Of course, it's a classic subject. There are other approaches. So another one which will be very useful in this talk is the approach using quivers and monads. This, as far as I can tell, it goes back to work of Beilenson, Dreyzet, Le Potier from the 70s and 80s, and was also revived in the context of string theory and D-branes by Douglas, Thiel, Rommelsberger, particularly say for the singularity C3 mod Z3, which is then if you deform it, you get the canonical bundle over P2. And this geometry appears as the geometric engineering of rank 1 E0 5D CFT, which was also discussed in recent work by Closet and Del Sotto. Yet there are other approaches to bundles over P2, for example, to directly apply toric localization, or the U-plane approach using the effective field theory. But I'll leave those aside for today. Okay, so this to proceed with the context of the quivers and monad, let me discuss or introduce quivers in some detail. I think they must have appeared, or they have appeared in various talks this workshop. But for completeness, a quiver, and for setting up the notation, a quiver consists of a number of vertices labeled by I in a set of vertices. Associated to each vertex, there is a Gates group U and I, and a stability parameter zeta I. And we'll use the convention that all the Fi parameters sum up to 0. There are a number of arrows between the nodes. I denote with kappa ij. Physically, they correspond to the bifundamental chiral multiplets. sorry, this gamma should have been a kappa. And then there is a gauge invariant superpotential, which only exists if there is a loop in the quiver. So this quiver, or the quiver quantum mechanics, gives rise to a set of D-term equations, which is as follows. So we have these fields phi, which map between the nodes, and they have to satisfy the following, namely that they sum up. If you take the sum of the outgoing arrows minus the ones corresponding to the incoming arrows, it should be equal to zeta I. And then we have the F-term equations in the case when the superpotential is not equal to 0. It has to be satisfied for all B and K and L. Okay. So then the quiver moduli space, I'll distinguish it from the earlier moduli space by a superscript Q. It's then a function of the dimension vector n, which is the vector of these n1, so in this case n1, n2, and n3, and the vector of the stability parameters zeta, and we need to satisfy all these equations. Okay. Then we say that the BPS index associated to this quiver is essentially it's the Euler number of this moduli space, and yeah, there's a formal theory behind it, which was nicely discussed by Pierre Bousseau in terms of DT theory. Okay. So one way to impose these equations is in favorable circumstances. It can be solved by a cut. You set to 0 all the arrows which are on one side. So we are, say, in this case, depending on the stability parameters zeta, one can solve these equations by setting to 0, say, the kappa 1, 2 arrows going between 1 and 2. And this would then also make the derivative to the p-potential Venice for the derivatives which do not involve those arrows. So the only ones which will be left to impose are the derivatives corresponding to the maps which have been set to 0. And in this way, one can determine the virtual dimension of the moduli space. One considers all the maps which are not set to 0, and then one subtracts the constraints, a term due to the constraints of imposing the superpotential, and then there's a gauge invariance and a U1 which is always there. Okay. So whether this can be done and how it is done is related to perfect matchings and braid tilings. Now a special stability is the notion of an attractor stability, which is the following. So given a dimension vector n with n1 and 2 up to the number of vertices, you choose these zeta i's as follows. So I give that superscript a for attractor, and then they are defined as follows: it's minus kappa ij times nj. And one way to think of it, it's as arising from the supergravity approach to BPS quivers. If you go to the attractor point, one can show that in the corresponding dual BPS quiver description, the DFI parameters satisfy this relation. And I think mathematically the stability is known as self-stability, arising in a paper by Tom from 2016. Okay, so we would like to set up BPS quivers for these Fano and toric surfaces. and kind of the key to given a surface find these or set up the BPS quiver are the so-called exceptional collections. So the exceptional collections provide a way to associate a BPS quiver to an algebraic surface. And for those surfaces like the toric surfaces and the Fano surfaces, exceptional collections are known, but they're not known for arbitrary surfaces. And the precise conditions are not completely clear to me. What are the precise conditions to have the right type of exceptional collection? But let me proceed by introducing this notion. So a sheaf E on the surface X is called exceptional if the X0 group of the sheaf is isomorphic to C, and when all the others for the higher X groups are empty. Okay. And then we can make a collection of such sheaves. This is an ordered set of exceptional objects running from E1 to some ER, such that the so that the X groups are equal to C for each K larger equal, sorry, this should be equal to C for all K larger equal 0, and then J smaller than I smaller equal to R. Okay, sorry for missing this detail. Now an exceptional collection is full if the Chern characters, if these Chern characters generate the K group of the surface. So then this is, if we assume that there are no one cycles or no odd cohomology, then this R here is just equal to the Euler number of the surface. And an exceptional collection is strong if the X is equal to 0 for all the I and J which are larger than 0. So this is, what I said before, not all surfaces give rise to exceptional collections. The strong full exceptional collections are known for toric surfaces, including P2. For Del Pezzo surfaces with K running between 1 and 8, and also for pseudo Del Pezzo surfaces. Let me say, I should have put a P there, for K between 1 and 6. Okay, so for these surfaces we can use this technique. To determine the quiver, we actually need, from the full strong exceptional collection, we need to go to a dual collection, and the dual collection is so I distinguish it from the original collection by this check mark. And then we require that the Euler number of the sheaves EI from the original collection and the ones from the dual collection are just equal to delta IJ. And now the nodes, now we built the quiver is constructed based on the data of this dual collection. So the nodes correspond to the elements of the dual collection, and we get a net number of arrows kappa ij, which is the difference of the Euler numbers of these there's the difference of the Euler numbers of the dual collection. So the gamma ij here are the Chern characters associated to the dual ones, and I should have added dual ones here too. These are all dual. And in addition, we need the notion of we need to determine the right superpotential, which one can establish using algebraic geometry or A infinity algebras or string theoretic techniques, say based on open strings. It's an important piece of data, but I won't go much into it here. You can find then the superpotentials in these papers. Okay, so then what one finds is for P2 is a very famous quiver. So it's the quiver with just 3 nodes, and and 3 arrows. That's the note. It's the indicated here. 3 arrows between each of the nodes, and the superpotential is the following combination. Okay, so this is basically how it goes. Is once the strong collection, the strong full collection is the following sequence of line bundles, the trivial line bundle, then the line bundles whose sections vanish on the hypersurface H, and then those with vanish at whose vanishing cycles correspond to 2 times H. And one finds then these churn characters for the dual collection. The first one is again the trivial line bundle. Then the second one is a sheaf with rank -2, or an anti-brane in physics language. And then the third one is again it's kind of line bundle with these churn classes. Okay. So now we see that if we add up these churn characters, they add up to 1, which corresponds to an we should actually say an anti-d0 brane, because the d branes will have a mostly negative churn character, and also we can so if we consider bundles of a positive rank and translate it to a dimension vector for quiver with dimension vector n1, n2, and n3, then there is an overall minus sign. Because of this mostly, because the churn character is mostly negative, somehow we get the coefficients, if you expand it in these gammas, comes out as negative. It's possible because this one has a minus 2. Okay, and the number of arrows, as I said, is equal to 3 between all the nodes, and there is to match to the quiver moduli spaces to the moduli spaces of P2. There's a specific charge of the zeta I, which sets to 0 all the maps which go from 3 to 1. So these maps are set to 0, and then so you just get maps from 1 to 2 and 2 to 3, which need to satisfy something. Sorry, this is my phone. Sorry about that. Okay, so that this is then if you just consider the quiver with the arrows from 1 to 2 and 2 to 3, which need to satisfy some relations that is familiar to maybe many of you as the Beilinson monad, which was just phrased in that way rather than as a quiver with a potential. Okay. So if this is this then implies this relation, namely that zeta 1 must be larger than or equal to 0, which should be larger or equal to zeta 3. And so if you then also kind of make the Giesecke stability of the bundles coincide with the quiver stability, then we have an agreement between the quiver moduli spaces and the moduli spaces of the quiver and the moduli spaces of the bundle. Okay. Are there any questions?
Are they stable things then all just sheaves on P2 rather than on local P2? I mean,
yeah, because the tangent bundle is ample. One cannot deform into the fiber, and that's why you can identify the sheaves, the stable sheaves on P2 with stable sheaves with torsion sheaves or two-dimensional torsion sheaf on local P2.
yeah, thanks. Yeah.
If the tangent bundle is not ample, then you would have deformations, and then it becomes a more harder problem.
So this works also for Del Pezzo surfaces?
Yeah, that's for Del Pezzos. It also works. I will say a little bit later in the talk. It gets, yeah, since the number of nodes is equal to the Euler number, especially for the higher Del Pezzos, it becomes quite involved. But there are exceptional collections. No. Other questions? Okay. So in this, an aspect which is not so relevant for the case of P2, because the Giesecke stability or slope stability, there is the polarization is always proportional to the hyperplane because it's just one-dimensional, and but for, say, Hitchable surfaces or the Pezzo surfaces, there is a positive or an ample cone in which you can choose the polarization. And then there is a canonical polarization, namely the one which is proportional to the Chern class, first Chern class of the tangent bundle. That one is distinguished maybe for one reason, because the generating functions simplify a little bit. Consider it as a distinguished point in the modulized space, or in the cone of the polarizations. So distinguish it here just with the subscript 0. If we translate this to the quiver stability data, zeta I use the superscript C to distinguish it from other choices of zeta. This corresponds to the following. It is a parameter rho, Will parameter rho, times kappa I j times nj, summing over j, plus a term eta I, and we take rho very, very large. If you're familiar with Giesecke stability, you know that you're first comparing a leading term in the polynomial of polarizations, and if those will be equal, then you compare a subleading term in the polynomial. So that's similar here. This rho is taken very large, such that if you compare the stabilities, then you first compare terms due to this term, and if they happen to be equal, then this subleading term comes into play. And now an interesting point to note is that this actually is just looks like what we had for the attractor stability a couple slides back. Where did I have, maybe right here? Here we had minus times kappa ij times nj, and here we have plus kappa ij times nj. So in that sense, it's opposite. It's basically, it looks like it's opposite from the attractor stability. Now we another requirement is that we had the requirement on the ordering of these stability parameters for zeta 1 and 3, which since the zetas are dependent on the dimension vector and therefore on the Chern character, it restricts the choice of C1 to this window for P2, namely this line between minus and 0, which can always be reached using isomorphism called the tensoring of the line bundle. But there are these, if you don't take this identification into account, on the Quivers side you would not find perfect agreement. But on the sheaf side you can always bring, there's this isomorphism, so you can always consider bundles in this window. Okay, so the natural question given this discussion we asked ourselves is, can we reproduce the invariants, the chi-y genera or the Poincare polynomials, which were earlier discussed, say from using Yoshioka's approach? Can we understand them or can derive them using the Quiver approach? This Quiver for the P2. And to address this question, we have taken the approach of the attractor flow trees based on the attractor mechanism, in particular the flow tree formula put forward by Alexandrov and Piolin, which was proven by Argus and Bousseau. So there were very nice talks by Bousseau also on the flow tree formula, and I don't have time and I won't go in as much detail. But we apply that in order to go basically to determine the BPS invariant based for these Quivers. So let me just indicate a little bit kind of the ideas behind this flow tree formula. So it's originally developed for string theory compactifications on R4 times a compact Calabi-Yau threefold, and then the n equals 2 supergravity in R4 that contains an intricate BPS spectrum of black hole bound states. So here we have kind of an artistic impression of black holes, and these positions of the black holes, they need to satisfy certain relations called known as the Denef equations. And in this supergravity solution, you need to solve solutions for the metric. Besides that, there are solutions for the scalar fields, and they vary over this space-time geometry. And basically the BPS equations, they require those scalar fields to go to special values at the black hole horizon. Okay. And precisely those scalar fields in the D-brane picture, they correspond to the stability condition. So you get this you can view it as that the stability conditions are a function of the three-dimensional space-time geometry. You pick them at some value at far away from the black hole, which is your stability you're interested in, and then these stability conditions or moduli they change and they go to specific values at the different black holes. Okay, so this is it's in general it's a very hard problem to solve, all these equations of motions. So then these flow trees were put forward by Denef and Denef-Moore, which is basically a one-dimensional approximation to this three-dimensional problem of the changes of stability conditions. So what how does this flow tree then look like? Well, we start out from infinity, very far away of these black hole centers. Then we follow we go down, and we go down as we follow the trajectory as if we are following to the single black hole, with which is all in a single center. So as if there was only a one black hole here in the middle, with charge gamma 1 plus gamma 2 plus gamma 3 plus gamma 4. And so we follow the flow until we reach the wall for all the charges moving to the left and to the right, and then we split. So if you would follow just say straight to a single black hole with the total charge. Sorry, I changed to capital values for gamma here. Then on this side of the flow, basically there will be no bound state, or this composition will be unstable, and on this state of the flow it will be stable. Okay. Are there any questions so far? Flow trees. Okay, so as I said, at the vertex at the wall here, we are at the wall. So this means that the central charge, which was introduced in the talk by Pietro Longhi, I don't think I won't introduce it again, but it's a map from the charges to the complex number set. Because it's a wall, then the imaginary part of Z of the charge going off to the left times the complex conjugate of the charge going off to the right is equal to 0. And for a non-vanishing contribution, we have the following conditions at the vertex. We have this first condition, which is basically saying that there is a wall, that you are changing from a stable site to an unstable site, and then there is another condition which is saying that your central charges must be in the same. If you are at the wall, so this would still allow for anti-aligned central charges, but you need that the central charges must be they must both be BPS particles, not one BPS and one anti-BPS. So you need to satisfy this second identity. Now, in favorable cases, basically the favorable cases are when the second condition is automatic. Then the flow can be determined from node to node without calculating the explicit flow along the edges, as explained by Pirik. And so, for example, for these geometric vector bundles and sheaves, we use this basically a large volume limit. So then the central charges, you can take them as being all aligned on the real axis. So if you stay in that regime, then this is always satisfied. The flow will not put you through a point where some central charge will move to the other side. So this is also at the vertex TV. Okay. Okay, any questions? Okay, so yeah, we used the flow tree formula by Alexandrov and Piolin, and what we found basically experimentally is that if we use the flow tree formula, then the input are the indices at the attractor point, and a priori, so we could have find different non-vanishing values for the indices corresponding to dimension vectors. But what we found that they are actually all equal to 0, except for the attractor, except for the nodes which have attractor value equal to 1. Just that's the standard. If you would have dimension vector 1, 0, 0, then the Euler number of the representation would give you of the modular space of representation will be equal to 1. So we can then make lists. Here on the left we have say the churn character, and on the right we have the corresponding dimension vector. So for churn character 1, 0, 2, instant number 2, we get dimension vector 1, 2, 2, and we find this 4-dimensional moduli space, and one can proceed. This table only shows the dimension vectors in which all the vertices are populated, or the dimensions on all sides are larger than 0. If one of the vertices has a vanishing dimension, then you can use the standard, say, Reinecker formula, and you can even go to rank 5. So So that's yeah, very striking. On the one hand, we can reproduce the Poincare polynomials of these moduli spaces in this way, and we find this special property that the attractor values for dimension vectors which appear in the flow trees are equal to 0. Okay, so that of course begs for an explanation, and what we found is that if you go to the attractor stability, so this is in a sense the opposite from the canonical stability we are considering, then there will be another set of maps which will be set to 0, and you will find a different dimension for the moduli space. And in fact, you will find that it is negative. So this in hindsight, this indicated that the attractor indices should be 0. And using terminology from Tom's paper from 2016, maybe we could call such a spectrum as a gentile BPS spectrum. Okay. So yeah, knowing this result, in a sense, you could also get the result using wall crossing. I think that was say what a bit related to what Pietro Longhi was showing in his talk. That basically you have an empty chamber, and you could get it from wall crossing. But here, we know all these indices at their individual attractor points. So the attractor mechanism, attractor flow tree formula is a natural technique to determine the indices, I think. So now I should say it's not true that all the attractor indices actually vanish. It's only the ones which are appearing in the flow trees for these bundles with a positive rank. I said earlier that if we take dimension vector 1, 1, 1, let me abbreviate it by delta, then it lies in the kernel of the antisymmetric form. And then one has to assign an attractor value for them, which is equal to this as minus y inverse times basically the Poincare polynomial of P2, which then is in agreement with the compact cohomology of the local Calabi-Yau. There was some further follow-up work. So in that sense, again, using terminology of Tom's paper, it's not that all the attractor or the self-stable objects have disappeared at the attractor point, but really most of them have. So it's quite an intriguing situation, I think. So we did consider many other surfaces for which there's the strong full exceptional collection to start with. For example, the Hitchable surfaces. Note that they are non-Fano if this m is larger or equal to 2. And another aspect I will mention it a little bit is that there are different phases in this case. The Del Pezzo surfaces, one can also set up basically go through the same techniques, and as well as the pseudo Del Pezzo surfaces. And we all found basically the same results, that we reproduced the calculations from the sheaves based on these generating functions, and the attractor values all vanish except for the ones of the pure D0 braids. Okay, so let me say a little bit about it. For the different phases correspond to different choices of exceptional collections. So for example, for the Hitchable surface F0, we have a two-dimensional middle cohomology generated by a base curve C and the fiber F. And then we can consider the following exceptional collection, which then gives rise, going through the dual collection and determining the arrows, gives the following quiver here with this superpotential. Whereas if you consider, say, a phase 2, then the exceptional collection is the following, and then you get this square quiver and the different superpotential. And they have slightly different kind of regimes of chunk characters they cover and stability conditions. But the main results go for. Okay. So yeah, both quivers reproduce the results based on sheaves with rank n larger than 0 in their regime of validity, and with all the attractor invariants vanishing except for those corresponding to the nodes. And for the zero brains correspond to this formula. Okay, and we can go to more intricate quivers for example for the higher Del Pezzo. For example, this is DP6, and yeah, you can go to even higher, but you get quite intricate quivers. Okay, so that brings me to my the conclusions. So in short, we have seen that for surfaces with a strong full exceptional collections, the attractor flow trees are an efficient and interesting technique to evaluate the BPS indices. And now the input of the attractor indices, we have much more freedom than we used. Basically, we saw that the indices are 0 for many of the dimension vectors, and we associated 1 to the nodes. We can apply the formalism with different numbers. So I think it will be interesting to explore to what extent this could be applied to other surfaces, Calabi-Yau freefold, or categories. And thank you very much for your attention and for organizing the workshop. Thank you.
Thank you very much. Are there any questions? Tom, please go ahead.
It's always me. So you have this, well, I guess the first question is, what's the mathematical status of this statement that the attractor invariants are what you say they are for local Del Pezzos?
I think there was I haven't studied the paper in much detail, but I think there was a paper by Pierre Decombe who basically proved this. Maybe other people in the audience can say more about it. But we saw it at the level of these dimensions, the dimensions of the moduli spaces. But
yeah, that was my other question actually. So that seemed slightly so. Of course, you're defining the moduli spaces slightly differently to how mathematicians would typically do it, because you're using compact gauge groups and putting a moment map, right, and then quotienting by the compact gauge group, which means that your expected dimension depends on the stability data.
Yeah.
Which it doesn't for us normally, right? I mean, well, at least I wouldn't know how to write down the expected dimension depending on the stability parameter. So anyway. So you compute the dimension and it's negative for the attractor stability condition. Is that right?
Yeah. So indeed, using the moment map and these D-term equations, it's at least for me clearest to see that some side of the arrows are all vanishing in order to satisfy the equations.
Right. So does that tell you that the moduli space is empty? Or?
Yeah. If you get a empty, a negative dimension, you have your gauge freedom is higher than the kind of your space without imposing the gauge freedoms.
Right. But does that actually imply that the invariant is 0? Do you know the invariant is 0 from that?
So I think that this count of dimension is still somehow expected count. It's assuming some independence between the condition imposed by the potential. And because you are not sure of that, you don't know if the moduli space is really empty. So.
Okay. Yeah, I think there remains work to be done on the formal DT side of that statement. But there was a yeah, papers by Sergei Moscovoy and Boris, and then Pierre Decomber recently, maybe also Pirik on the mathematical side.
Thanks.
Any other questions or comments? Right, if not, let's thank the speaker
Actually,
again. Oh,
can
sorry.
I ask a,
Yeah,
sorry,
go ahead.
No, can you comment on your last comment, actually? What do you mean by, you mean compact Calabi threefold or the extension to other cases? Or to more general local one with more devices, exceptional devices?
Yeah, that's a possibility for, well, one could say, yeah, one could say consider surfaces for which not the instanton branch is not the only branch in the solution space to the Waffa-Witten equation. You get, say, contributions from the Seiberg-Witten invariants. Would it be possible to, yeah, to set up a quiver for those surfaces, which also kind of reproduces the same Euler numbers of those, or the coefficients of those generating functions which appear in those cases, or yeah, for Calabi-Yau threefolds. Yeah, you could say, if you, I'm not sure to what extent this. Yeah, you would say if you take, for example, the quintic, you would like to apply the formula and say, can you determine the attractor invariance for say a compact Calabi-Yau threefold?
But in terms of quivers, is there an example, for instance, of a surface which is not Fano, where you would have still a quiver description of the sheaves or something?
Well, the quiver descriptions are all in terms of bound states, where you kind of know the constituents of the bound state. For a compact Calabi-Yau, you get an infinite number of potential bound constituents. So once you select your constituents, you can set up your quiver. I think, but a priori, I think for each electromagnetic charge, which gives a central charge in your chosen half plane, you would associate a node in the quiver. So yeah, you would get kind of maybe, I'm not sure whether that makes sense, but you would get quivers with an infinite number of nodes, and usually most of the, or all but a finite number of vertices will be populated with a non-vanishing dimension. And this is a bit wild speculations, but in that sense, I think you can you could apply these formulas for bound states.
Thanks.
What about quivers for orbifolds, just groups acting on C3? I guess that you could, that should be possible, right?
Sorry, which ones?
Well, just like take finite subgroup of SL3 acting on C3. That gives you a quiver, like the Mackay quiver.
Mm-hmm.
And I guess there's still an attractor point, and we don't know what the attractor invariants are, I suppose. Right, so C3 mod Z3 would be your local P2 example, right? That would be the same thing, but there you could take different groups.
In general, might not have a resolution. Well, for C3.
But it doesn't matter, you don't need a resolution, right?
Yeah, no, it's use some equivalent sheaf or something, you're counting.
Yeah, I mean, you always have a quiver, and you can do DT theory.
Is the BPS spectrum known? Is there something known about the DT invariance?
Pass. I don't know. I mean, in examples for sure, yeah. But Sergei's here.
Yeah, so there are some conjectures in our paper with Boris concerning C3 modulo Zn and this kind of stuff. but all of them, as well as C3 modulo Z3, are, I suppose, still open. So we could produce only calculations for small dimensions in these cases.
But there is no conjecture for the attractor. So, no, very simple.
No. No, the point is that in all those cases where we could make calculations, we could also make a conjecture, a general conjecture for attractor invariance, but we couldn't prove all these formulas.
Thanks. Hi, Sergey, by the way.
Hi.
Right. Any other comments or questions?
I have a general question well, maybe to anyone in the audience. What is known about local fourfold? I mean, there are quivers, which are like generalized quivers. Some of them have been studied also in the math literature, I think, by some students of Joyce, and I don't remember whom. But so those are like quivers where, you know, you need to count. You have a bit more structure, for instance, in terms of a local fourfold that would have a resolution. You would have kind of your 4 kind of categories. So there are more X groups, more structure. So in particular to the X1, you would assign an arrow and then a second type of arrow to the X2 between objects. So those are generalized quivers, which are nice also from physics, but I haven't seen that much studied. It's not one PhD thesis I've seen. Do you know anything about that?
I mean, I know Dominic Joyce had a student called Yanting Lam,
Right. Yes.
and he has a thesis with lots of examples calculated of these things. But I don't know whether people, of course, there's DT theory for CY fourfolds these days, and I don't know whether these have been calculated. Yes, I think they have. I went to a talk recently.
Right, I guess, are there any other questions? All right, so let's thank Jan again for a great speech. Now, Tom or Andrea, would you like to give some closing speech?
Definitely Andreas. Andreas should do it.
Yeah, I wasn't going to unmute myself. I guess now I must. Oh, thanks everyone for coming. I think I really enjoyed the talks. Yeah, it was really great workshop. I've learned a lot, and it was great to see the attendance. And we had lots of great discussions. And actually, if you want to stick around now, we can keep the room open for discussions, as we did in most of the other days. And if not, thanks very much. And I think there's some lingering hope we might wish to repeat this, possibly post next year. So yeah, stay tuned.
Yeah, it's too bad it couldn't be here in reality. The weather is gorgeous.
Yeah.
It would have been, yeah. Would have been nice.
Sorry, we should stop the recording.
Okay.
Oh,